A steel cable snaps taut. A bridge deck settles under the weight of rush-hour traffic. In the physical world, massive structures experience immense stress, tension, and compression every second they stand. We can measure the sag of the steel or the strain on the concrete, but the specific forces keeping the structure from collapsing are invisible to the naked eye. Engineers view this transmission tower as a dense network of intersecting points, conduits for the invisible, continuous forces passing through them. To calculate those forces, engineers rely on a specific analytical tool, the free body diagram. A free body diagram is an exact mathematical accounting system. It tracks every vector acting on an object. To build one, you have to conceptually erase the physical universe. You take the physical object, strip away its environment, and replace its physical constraints with a strict translation of mathematical vectors. We cannot calculate equilibrium until the object is mathematically detached from reality. Understanding a structure's stability requires total isolation. That isolation starts with a strict translation protocol. Physical supports must be deleted and replaced by equivalent reaction forces. The guiding principle is simple. The specific direction of physical support restricts movement is the exact direction of the reaction vector you must draw. Consider a basic roller support. A roller allows an object to slide horizontally, but it prevents the object from moving downward. Translated into algebra, that vertical restriction becomes exactly one unknown vertical variable. Now replace the roller with a pin or hinge joint. This connection prevents vertical movement, and it also restricts horizontal sliding. We translate the pin into two unknown variables, one force component along the x-axis and another along the y-axis. Finally, look at a fixed wall support. It restricts horizontal sliding, vertical sliding, and any rotation. This generates three mathematical unknowns, two linear force vectors, and one rotational moment. Moving from two-dimensional planes to three-dimensional space scales this logic up, reaching a maximum of 6 unknown variables for a completely fixed spatial support. The physical geometry of the support strictly dictates the number of unknown variables in our mathematical puzzle. This upper schematic demonstrates a standard 2D engineering problem, a beam embedded in a fixed wall on the left and propped up by a roller on the right. To translate this, we execute the protocol, mentally delete the wall and delete the physical roller. The resulting free body diagram is shown below it. The fixed wall is replaced by horizontal force HA, vertical force VA, and rotational moment MA. The roller is replaced by a single vertical vector RB. We apply the exact same logic to a 3D scenario. This top diagram shows a boom held in place by two cables and a ball and socket joint at the base. We delete the physical cables, and we delete the physical socket. The lower diagram reveals the free body equivalent. The cables become internal tension vectors TCD and TBE. The ball and socket base becomes three independent reaction coordinates, AX, AY, and AZ. Once the free body diagram is drawn, the physical object ceases to exist. The physical forces are now a problem of pure geometry and algebra. With the unknowns exposed, we apply the laws of static equilibrium to solve them. Mathematically, this means the sum of all linear forces must equal 0, and the sum of all rotational moments must equal 0. In a concurrent force system, all vectors intersect at a single point, meaning no rotation can occur. But in a non-concurrent system, forces apply leverage across a distance. This technical drawing of a non-concurrent system shows a board held by a cable and a hinge. It requires the tactical use of rotational equations. Our unknown variables are the vertical and horizontal forces at the hinge and the specific tension inside the cable. Because a moment is force multiplied by distance, we can use a mathematical trick. Look at the equilibrium equation below the figure. By calculating the sum of the moments exactly around point A, the pin joint, the physical distance for those specific hinge forces becomes 0. Multiplying the unknown hinge forces by 0 eliminates them from the equation entirely, isolating the cable tension, T, so we can solve for it immediately. These equations function as active mathematical tools, allowing engineers to systematically eliminate variables and solve for unknown forces. How do engineers scale these calculations for a massive system containing hundreds of interconnected beams, like this bridge? Analyzing this requires three extreme engineering idealizations. We assume all joints are frictionless pins. We assume loads are applied only at those exact joints. And we assume the weight of the steel members themselves is negligible compared to the loads they carry. When you apply these assumptions, every single beam mathematically reduces to a two-force body. The logic dictates that if only two forces act on opposite ends of a rigid bar in equilibrium, they have no choice but to be equal in magnitude, opposite in direction, and perfectly collinear. Because of this strict alignment along the axis, the member experiences pure tension or pure compression. Bending moments are entirely eliminated from the math. These extreme idealizations are deliberate abstractions. They take infinitely complex structural networks and render them solvable. Structural analysis relies at a strict balance between the unknown variables we possess and the equations we have the power to write. We use a formula to see if a truss is solvable by statics. 2j equals m plus 3. J is the number of joints, generating two x and y equations per pin. M represents internal member forces, plus 3 standard external support reactions anchoring it. This determines static determinacy. If the number of equations perfectly matches the number of variables, the physical structure is completely solvable using only algebra. Starting with heavy physical chaos, we use free body diagrams to strip away the environment, reducing raw steel into a predictable matrix of isolated equations. The free body diagram acts as the primary interface between physical reality and the mathematical models used to design our world with absolute certainty.